by seeing if there's any questions on what we did yesterday. I'll be talking more about complexity theory today, so hopefully you absorbed the basics yesterday. No questions? Okay, so just to remind you, complexity theory, as I characterized it, is the study of the computational difficulty of problems. And the goal, as I said, is to classify whether problems are easy or hard. Now, yesterday we talked about what it means for a problem to be easy, right? It's in the complexity class P for something that's easy on a classical computer, or BQP for something that's easy for a quantum computer. And maybe it's kind of obvious if somebody gives you a problem that if you want to show it's easy, the natural way to do that is to find an algorithm for it, right? A classical algorithm or quantum algorithm. But that leads to the question, so a problem is hard means that it's not in P or BQP, but how would you show that, right? Obviously, you can't present a non-algorithm. That doesn't even make sense. That turns out to be a very difficult problem, and it's not something that we really know how to do in general. But one thing that people have managed to do is to classify different kinds of hard problems. And by understanding something about that classification, you can get a good indication that a problem really is hard. So in particular, one thing that one complexity class that people talk a lot about is the complexity class called NP. And so this is going to be a class of problems. Well, as you'll see, it includes some easy problems and some hard problems, presumably. So it's a class of languages that have the following property. So there's supposed to exist a verifier algorithm and this verifier takes two inputs, x and w. So x is going to be the instance, and w is another number. And we want this algorithm to have three properties. So first of all, it should run in a time that's polynomial in the size of x. When the size of w is also polynomial in x. So second, if x is in the language, there should exist some wx such that this verifier applied to x and this special wx outputs yes. And it should be that the size of wx is polynomial in x. And then finally, if x is not in the language, then for all w of polynomial size, it should be the case that v of xw will output no. Okay, so this wx is known as the witness. For the yes instance x. Okay, so let me unpack this definition for you a bit. So the conceptual idea of the class NP is that it's the class of problems that are easy to check. Okay, But you need some extra information to check this answer, and that's this witness. Okay, so so the idea is that V is the checking, the verifier, the checking thing, and so if you're given a yes instance, there's supposed to be a witness that proves that this is really the correct answer. And that's this witness WX. And then you run the verifier algorithm, and it's supposed to output yes. On the other hand, if it's a no instance, then there shouldn't be any way to prove that it's the correct answer, because that the answer is yes, because it's not. So that if you run the verifier with any witness, then you'll output no. OK? And let me give you a concrete example of a problem in NP. And so that's the problem KSAT, for K satisfiability. So the instance is a Boolean formula. So Boolean formula is one that acts on variables. So there's going to be n variables xi. And these are binary variables, which you can interpret as true and false values. And the output is also going to be true and false. And so, so you combine these variables using the usual logical things, or, and, not. And in particular, the formula is of the form C1 and C2 and C3 and ... Cm. For the M clauses, Ci, and each Ci is the OR of K things called atoms, which are the form have the form. So each of the atoms is the form either XA or not XA. Here, maybe I should put it in quotes to distinguish between this or and that not. Okay, so so each of these things has K pieces. That's why it's KSAT. So for instance, for 3SAT, a clause could be, x1 or x2 or not x3. Okay, and that one's satisfied if x1 is true, or x2 is true, or x3 is false. Okay, does that make sense? And then, because we have the and of all of these clauses, we want all of the clauses to be satisfied. And so this KSAT formula evaluates to true. The atoms are either x's or not x's. Okay, so basically each atom is a statement that some variable should be true or that it should be false. But because we have the or of them, not every one of them has to be in the case. Oh yeah, and so KSAT is a yes instance. Sorry, we have the formula is a yes instance if there exists some assignment to the variables such that this formula evaluates to true. And it's a no instance when there isn't such a satisfying assignment. So, so it's easy to see, I think, that this problem is in NP, right? So what's the witness? The witness is just the satisfying assignment. Right? Does that make sense?
Is that a case where
Oh, absolutely. So let's see. So let's take a very simple example. Well, OK, so the easiest thing is just to take one set. OK, so k is just going to be 1, just for the very easiest example. And so then each of these clauses is just a single thing. So for instance, the first one, and I'm just going to take one variable, x1. And the first clause will be x1. The second clause will be not x1. OK? Yeah, so you're allowed to repeat variables. In fact, it's not interesting if you don't repeat variables. Now, in that particular case, x1 and not x1, it's very easy to see that it contradicts each other. But in other cases, it's much harder, right? And when you have ors, there's a lot more possibilities, of course. But hopefully that answered your question. Yeah. OK. Right. No, they don't have to be. So there's n variables here and m clauses. And so we're having a total of m times k atoms, right? But n could be much smaller than that. If it's larger than that, there's not really any point. I mean, it could be larger than that. You don't use all the variables. And some get repeated anyway. But that's kind of silly.
So the thing that goes into the language are these formulas, not the actual.
So yeah, that's right. So the instance is the formula, right? Okay, and the assignment of values to the x's. I mean, so the formula includes, the names of the variables, obviously, because how else are you going to describe it? But the assignment of actual values to the variables, that's your potential witness. Okay. Yeah.
So maybe you're about to go into this, but when we're talking about this having some scaling property with the size of the input, what's the size of the input? Is k?
Right. So the size of the input is the total description of the formula. So basically, in order to describe this formula, how do we describe a single clause? Well, we have to list three atoms, or sorry, k atoms. And I guess each description, so each atom is gonna take log of n plus 1 bits to describe. Okay, because we have to say whether it's the xa or the not xa case, and we have to give what a is. Okay, and so then we have k of those per clause, so that's k times log n plus 1. And then we have m clauses. So this is the total size of the formula, of everything that we need to describe the formula. Basically, the point is that, but n, remember, is going to be less than m times k anyway. I mean, because otherwise there's not much point. And so really, basically, we're saying that it could be the size of the thing is basically m times k. And we want something that's polynomial in m and then k. When I say polynomial, that's what I mean. Okay, and it's easy to see that the verifier is in fact polynomial in that, right? So if somebody gives you a potentially satisfying assignment, an assignment that they claim is satisfying, how long does it take to check that? Well, I mean, each clause. So k is usually constant, I should say. So it's actually m that's really the variable here of the size. So each clause takes constant time. It takes some order k time to evaluate that clause, whether it's true or false. And then you take the end of those. So that just takes, again, linear time in m. Yeah?
If I was to find an algorithm, not a checking algorithm, but an algorithm to solve this, do I need to be able to produce these witnesses? Or does it just suffice to be able to say yes or no and be correct every time?
Right. So let's think about our definitions, right? So our definition was that an algorithm decides the problem if it outputs a yes or no, okay? And it doesn't have to do anything else. So yes, if you come up with an algorithm that just says this formula does have a satisfying assignment or doesn't have a satisfying assignment, that by itself is good enough. But as it turns out, if you have an algorithm that does that for any KSAT problem, you can actually find a witness. So how do you do that? Well, what you can do is you can eliminate variables. So you say, well, OK, I'm going to take this formula, and I'm going to say, suppose that x1 is true. OK? And then I plug that in everywhere. And maybe that will make some of these clauses true automatically, because they're OR of x1 or something. And so I can just eliminate those. And maybe I'll find that it doesn't work at all, because somehow there's a contradiction already. In that case, I know that's not right. But if not, then I can just take the reduced formula that I get by plugging in x1 equals true and running this algorithm on that. Okay? And if there is a satisfying assignment, then I know it was OK to pick x1 equals true, and then I can go on and do that for the rest of the variables. And if there's not a satisfying assignment, but there was one for the original formula, then I know that I have to take x1 equals false. And then I can, again, plug that into here and reduce the formula and go on from there. Okay? So the answer is yes, it only needs to say yes or no. But actually, that's enough to give you the witness.
Is that true for every problem?
No. And in particular, something that's of interest to this class is that, I mean, if you start to think about quantum problems, just saying yes or no frequently is not going to be enough to tell you, kind of what the answer is. So there's this is really beyond what I was going to talk about. But the quantum analog of this, the witness is a quantum state. And examples of problems in this quantum analog called QMA are like finding the ground state energy of a Hamiltonian. Okay? And just saying, yes, the ground state energy is below some value is not enough to actually tell you what the ground state is, even by some reduction of what I said. At least we don't know how to do it. That's maybe a better way of saying it. OK? Any other questions on the definition of NP and the example? Yeah.
The word witness, is it used differently here than, say, in the context of entanglement witness?
No, it's kind of the same. So the idea of a witness in this complexity theoretic sense, the witness for NP is something that proves that this is the case. So it's kind of testifying that this problem really is a yes instance. Whereas an entanglement witness is something that proves, that kind of testifies that you really have entanglement.
But it seems here,
In that case, it's a measurement that you can make.
but the witness here is kind of like a solution, while in the entanglement case, it's like a
That's right. But in this example, there's kind of an obvious problem for which the witness is a solution. But you can imagine other problems in which that's not really true. And the definition doesn't say that, right? It just says, well, there's some verifying algorithm. Okay. But frequently, it's the case conceptually to think of it as being a solution. It's true. Okay? OK. So we know KSAT is an example of a problem in NP. But how hard is it? I mean, there are going to be some problems in NP that are going to be very easy, and some problems that are not. So maybe the obvious thing I can say is that P is included in NP, right? Because any problem where you can, in polynomial time, figure out the answer yourself, well, the verifying algorithm is then just run that, and you don't really need a witness. Anything works as a witness. Ignore the witness, and then run the algorithm that finds the answer. Right? And that will satisfy this definition. Okay? So some problems in NP are going to be easy. Do we know KSAT is one of them, or is KSAT a hard one? Well, if you look at the very small values of KSAT, like 1 sat, for instance, 1 sat is clearly going to be easy, because it's just saying all of these things have to be true. Right? So you know exactly how to assign everything. And unless there's a contradiction, like the example I gave, then it will work. And if there is a contradiction, then you know it won't work. It's a little less obvious, but it turns out that 2 sat is also easy. But 3 sat we don't know any way to solve that. We don't know an efficient algorithm. And more than that, we have some pretty good evidence that there is no such efficient algorithm. And in particular, what we know is that 3-sat and higher values of k are as hard as any problem in NP. So how can we possibly know that? Well, so the idea behind this is something called the reduction. So we say that a language L reduces to another language M if there exists some polynomial time function that maps words to words. So it's mapping 0, 1 star to 0, 1 star. Such that x is in L if and only if f of x is in M. Okay? So, so f doesn't have to be invertible. But, sorry, this is not right. Yeah, this is right. OK. Yeah, OK. F doesn't have to be invertible, and in particular, it doesn't have to be easy to compute the inverse, even if it is invertible. But the point is that given any instance, which might be a yes instance or no instance for L, we can convert it into an instance of M. And if it was a yes instance of L, it's now a yes instance of M. If it was a no instance of L, it's now a no instance of M. OK? And then we say that a language is NP complete if the language is in NP, and for all languages in NP, they can be reduced to the language M. Okay, so this terminology is maybe a little bit confusing in that the motivation here is that the language M is at least as hard as L. So you're reducing to something harder. But this is reducing as in the mathematical sense of reducing to something that you've already proven. And let's look at this definition, and why does it mean that M is at least as hard as L? Well, suppose you have an algorithm to solve M. Okay? Then I'll claim you also have an algorithm to solve L. Why? Well, suppose you're given an instance for L, x. Then what you can do is you can plug it into this reduction. You get an instance of M, and then you solve M, right? And then you know that that if f of x is in M, then x was in L. And if f of x is not in M, it's a no instance, then x was a no instance of L. Okay? And so you solved L as well. Okay? But it doesn't have to go the other way, because as I said, f doesn't have to be invertible, and in particular, it doesn't have to be easy to compute the inverse, even if it is invertible. Okay.
So proving k-sat solves and finding algorithm to solve k-sat equivalent to proving k-sat.
Yes, but I haven't said the relevant information yet, which is this, which is that so this is known as the Cook-Levin theorem, which is that 3-sat is an example of an NP-complete problem. Okay, and yes, so if you could find an efficient algorithm that would solve, so 3-sat is an example of an NP-complete algorithm. If you can find an efficient algorithm that could solve it, that means that for every language in NP, you could reduce it to 3-sat, and then use your algorithm to solve it. So you could then have an efficient algorithm to solve any language in NP, which would imply that P is equal to NP. Yeah?
That's kind of surprising because higher K are also NP, right? Because we can check that.
That's right. That's right.
So like 10-sat reduces to 3-sat.
That's right. So it's maybe a little bit surprising, but there's a lot of freedom. Remember, this is the language of all 3-sat formulas. So what you can do is you can add extra variables. You can kind of rearrange the clauses to introduce new things, and yeah. So in fact, you can come up, given any 10-sat formula, you can come up with an alternative formula that's a 3-sat formula that is kind of equivalent. Yeah.
It's not too difficult to believe you can do it for any K-sat problem. But outside of K-sat problems, you can extend this to 3-sat is complete to any NP problem.
Any NP problem, that's right. And I don't want to prove it. That's maybe a little bit more involved than I have time for. But it's not incredibly hard to prove. The basic idea is this, that so given any NP problem, well, you don't know very much about it besides that it's an NP problem. But that means that there's this verifier function. OK? And you can write this verifier function. You can kind of rewrite it as a Boolean formula. In fact, you can rewrite it as a 3-sat formula, a formula with clauses of 3 atoms, because the formula, so the verifier is broken down into a set of gates. And each gate you can think of as having 2 inputs and 1 output. And those are your 3 variables that appear in this clause. Okay? And so you can make the statement of, does there exist an input, W, that has V output yes? You can convert that into a satisfiability formula. Does there exist an assignment of variables that makes this a corresponding formula output true? So that's the intuition of the proof. And actually, the rest of it is just kind of technical detail. That's the main intuition. Okay? But yeah, it's a pretty amazing result, and it's considered basically one of the cornerstones of theoretical computer science. Maybe along with statements about undecidability of halting problem, things like that. So it's definitely a big deal. OK. So then let me quickly mention where quantum computers fit in here. So I already told you, so P is inside NP. And it's a big open problem whether P is equal to NP. Most people think that P is not equal to NP. So the Venn diagram then looks like this, where there's some problems outside. And, the NP complete problems would be over here, because if you can solve one of them, the whole thing would be inside P. But there do seem to be problems outside of P that are still in NP. And so proving something that something is NP complete is considered very strong evidence that it's actually a hard problem, even though we can't actually prove that. Okay? And then where does BQP fit into this? Well, BQP also includes P, because you can do anything on a quantum computer. You can do anything you can do on a classical computer. But we think it looks like this. So we don't think that BQP includes NP, that NP complete problems are still hard on a quantum computer. On the other hand, it does seem to include some problems, like we'll talk about factoring tomorrow, that are in NP and not in P. And moreover, we think it includes some problems that are not even in NP, that there's no efficient way to check the answer to this problem on a classical computer. But you can still find the answer efficiently on a quantum computer. So simulating quantum systems kind of is a standard example of that. So this gives you an idea of how these complexity classes relate. Yeah?
Is factorizing prime numbers NP complete?
No.
No, okay.
If it were NP complete, then this picture would have to look different, right? Other questions? OK. So So as I said, P versus NP is a major open problem in computer science. We don't know for sure what the answer is. And I don't think at the moment anyone has a really good idea of how to prove it. But so that's a little bit annoying, because you'd really like to be able to at least prove that some problems are hard. So what people sometimes do is they look at kind of a simplified model called the Oracle model. And the advantage of this is that you can actually prove stuff about hardness. So an oracle is basically a black box function. And so the oracle is going to take some input, and it's generally, doesn't have to, but it generally gives a 1-bit output. We don't know anything about how O is computed. It's just some machine. We feed in a number to it, and out comes an answer, 0 or 1. Okay? And in the Oracle model, we want to, okay, so we say we make queries to the Oracle. Yeah.
The Oracle characterized by the size of its input, or you can allow the input size to vary?
Yeah, I mean, I guess for a given oracle, generally there's going to be a fixed input size. You're right. And in a moment, we're going to consider kind of classes of oracles. And this may be the best way to say it. So anyway, then we make queries to oracles by giving them some input and getting the output. Okay, and that's all we can do with oracles, is we can give them inputs, make queries to them. And so what we want to do then is to compute some property. We're given this oracle, and we'd like to compute some property of it. So let f of O be a property of the oracle. And then in this oracle model, we compute something called the query complexity of this property. And the query complexity is simply the minimum number of queries needed to determine this function. Okay. So let me give you an example. So this is going to be a promise problem. And the promise is that the oracle, which maps n bits to 1 bit, is either constant, which means that the output is the same for all inputs, or it's balanced, which means that the number of 1 outputs and the number of 0 outputs are the same. So if we look at the set of x such that O of x equals 0, that's the same size as a set of x such that O of x equals 1. Okay? And then the property is, say, with 1. Okay? So does this make sense? The Oracle model in general and the example in particular. Okay. Now in this query, in this Oracle model, you can talk about actually a couple of different kinds of query complexities. For this particular problem, I want to insist that the answer is always correct. So there's not going to be any randomness necessarily involved here. I want to say get this answer with no chance of being wrong. Okay, so if we do that, how many queries do we need to make to this oracle to figure out whether it's constant or balanced? 2 to the n minus 1, okay? So we make 2 to the n minus 1 queries. Let's say we'll try the first 2 to the n minus 1 inputs and see if they're all the same or not. Yeah, so if we only do 2 to the n minus 1 queries and find that they're all the same, then we actually still don't know, right? Because it could be that it just happens that all the inputs we tried happen to all be the same. Because each of them, in the balanced case, each of them, there's 2 to the n minus 1 possible. There's 2 to the n minus 1 inputs that give that output. So if we got very unlucky and they happened to pick all of the same ones, I mean, it could be that we'd find that 2 of them were different, and then we'd know. But if we get unlucky and it happens to be all the ones that have value 0, for instance, then we wouldn't be able to tell. So what we actually need is 2 to the n minus 1 plus 1 queries to say with certainty. Now, if you're willing to go to randomized complexity and just say with very high probability, then you could use many fewer queries. Because picking at random, the odds that you just happen to always pick ones that had the same value is unlikely if it's balanced. Whereas, of course, if it's constant, then that always happens. But let's focus on the exact complexity for now. Okay? Okay, so again, everything making sense so far? Any questions? Okay, so a couple of points that I want to make about the Oracle models. So the query complexity only counts the number of queries. Okay, so it doesn't care about how many gates you have to do in between. So you're allowed to make a query and then do some really complicated calculation, and then make another query, and then make another query. And it's only the 3 queries that matter there. The long calculated computation, we're not counting that. But in practice, a lot of times, the algorithms that people come up with, Oracle algorithms, the gate complexity of those algorithms is not too much larger than the query complexity. So query complexity can provide a good guide to the kind of the regular complexity. And that's important because if you have an Oracle algorithm, here, this I want to write down. So given an Oracle algorithm, a query algorithm, you can convert it into a regular algorithm by substituting a kind of an explicit function for the Oracle. Okay, so yeah, so for example, here's kind of a trivial, well, sub-example, where one way we could get an oracle like this would be if this O of x is equal to a xi plus b. Okay, where xi is the ith bit of x. Okay, and maybe this is calculated through some more complicated, circuit, and we don't really know the details. But we know from the structure of the circuit that somehow it's going to come out to be of this form. And maybe we don't know a, b, or I, but we know it's going to be of this form. Okay, so what we could do then is if we have an algorithm that solves this oracle problem, is every time we're making a call to the oracle, we plug in that circuit that calculates this, and then just run the oracle algorithm otherwise unchanged, right? So the oracle is a black box, but we're allowed to replace the black box with something where we actually know what's inside of it, and it still works the same way. Okay? So if we have an oracle algorithm, then we will have a regular algorithm to solve this problem with the explicit function. But unfortunately, bounds on the oracle algorithm which means bounds on the query complexity, lower bounds, don't necessarily translate into lower bounds on the regular complexity. And why is that? Well, the reason is that while it's certainly the case that you can make an oracle algorithm into a regular algorithm, you can't necessarily go the other way. And the reason is that the regular algorithm might take advantage of what you know about the structure of the problem. Okay? So for instance, in this sub-example, so in the oracle model, we said, well, we have to try 2 to the n minus 1 plus 1 queries, because we have no way of knowing which things to try. Right? Everything is kind of equally likely to be the half that's all 0. But in this case, that's not true, right? By trying the inputs, 1 and then all zeros, if I happens to be 1, we'll you try 1 and all zeros, and then, let's start with all zeros. Okay, so this part will be 0. That tells us what b is. Right? And then we try 1 and all zeros, and that will tell us if I happens to be 1, or happens to be the first variable. And then 0, 1, and then all zeros, and then 0, 0, 1, and all zeros. And trying 1 in each place, well, we have n bits, so we only have to try n times, rather than this 2 to the n minus 1 plus 1. Or maybe n plus 1 in the worst case. Probably you can do better than that. Probably you can do. Yeah. But anyway, this is a simple algorithm that's much quicker than this one. And the reason is that you're taking advantage of what you know about the structure of the problem. Okay? Whereas the black box, it has no structure. That's kind of the definition. Okay? So black box model, oracle model, is good in cases where you think there really isn't structure that you can take advantage of. And not so good when there is structure. But of course, just because you think there isn't structure doesn't mean that there actually isn't. Anyway, despite this, people like to prove lower bounds on the query complexity. It sort of gives you some guidelines for what to expect about the complexity of other algorithms, even if it's not actually telling you definitely. And it can definitely guide you towards how to find those algorithms, right? So obviously in the case where you can find a good oracle algorithm, then yes, you apply that and you're done. But in cases where you don't find an oracle algorithm, it tells you that if you still want to look for an algorithm, you have to take advantage of the structure of the problem in a way that the oracle algorithm does not. Okay, so that tells you where to look. So any questions on the oracle model?
That thing's not
Well, it doesn't even make sense. This is a totally different model, right?
Really?
This is so. OK, so you can define complexity classes relative to an oracle. And depending on what you say is the yes answer. So if you say balanced is the yes answer, then yes, this would be an NP relative to this oracle, because what's the witness is two inputs that have different outputs, right? Then you know it's balanced, given the premise. Right. So there is this asymmetry in the definition of NP, that for the yes instance, you're supposed to have a witness. For the no instance, you don't have to have a witness. So you can also define a kind of the flipped complexity class called co-NP, where you're supposed to have a witness for the no answer. So like unsatisfiability is an example of a co-NP problem. Given this formula, tell me yes if there's no satisfying assignment. OK, but maybe then we're ready to move on to quantum oracles for the last 15 minutes.
Co-NP?
Yeah.
Okay. What's the witness?
Well, so for co-NP, the witness is supposed to be the case when you have a no answer. So it's a satisfying assignment. The no answer is there is a satisfying assignment. It's just the same. It's the same problem, flipped everything. Yeah. OK, sorry, that was a digression. So quantum oracles. What we like to do is compare classical oracle query complexity with quantum query complexity. So in particular, we want a way to make the quantum version of a classical oracle. And that's straightforward to do using stuff we did last week. The oracle, as I've described it, is taking n-bit input and giving it a 1-bit output. To make it quantum, we want to make it reversible. So how do we do that? Well, we keep a copy of the input. So, and then, of course, we have to put kets around everything. That's it. So oracle is going to be now a unitary. And it takes two inputs, basically. So one of them is the thing that we were thinking of as the input before. And the other is going to be some answer bit that's used to record the answer. And the output here is, O of x plus a. OK. And again, this only applies to basis states. This is what happens to basis states. If we're applying the oracle on a superposition, we can extend that by linearity. OK? So this definition makes sense. And you usually draw them something like this. You'll have the input register, and you'll have a big box for the oracle. And then here we have x. Here we have O of x plus a. OK?
You should be able to do a unitary without having the x of a. You kind of have to.
I mean, yes and no. So, I mean, there are things you can do, but you have to be a little careful when doing such things. I mean, so for instance, suppose you have an oracle that instead of taking from n bits to 1 bit is just doing some permutation of the inputs, right? So it's a one-to-one function on n-bit inputs. But you still would not like to have it as an oracle that maps x to O of x without any kind of ancilla. And the reason is because now you're presuming, I mean, so the reason is that doing that is kind of presuming that the inverse permutation is also kind of easy to calculate in the same sense as the oracle. So you're kind of giving something extra power by doing that. So you usually are careful not to, and you just do it this way, even when it really is, possible by dimensions to do it. This is the most straightforward thing. Is if you have a circuit, that implements a classical function for O, then you can easily make this. Making the thing that doesn't have any ancilla, that's not necessarily easy to do. Okay? So now what we're going to do is try to come up with a quantum algorithm for this oracle problem. And I claim that there is such a quantum algorithm that works with 100% certainty and uses only 2 queries to the quantum oracle. So that, of course, will give the quantum query complexity. So how does that work? Well, so this is known as the Deutsch-Jozsa algorithm. Deutsch. So we're going to have n plus 1 qubits. So these are n qubits, and this is 1 qubit. And the first thing we do is the Hadamard on these top n qubits. And then we do an oracle call. So the oracle call is supposed to involve n plus 1 qubits, so that's where this extra one is coming in. And then we do a z down here. And we do another oracle call. And then we do Hadamard again up here. And then we measure these. And so then based on this output, measurement output, so if the measurement output is all zeros, then we decide it's a constant function. And for any other output, any other measurement output, we say it's balanced. Okay? So I will explain why the circuit works in a moment, but do you understand the structure of the circuit? Yeah. Yeah, this is a promise problem. So we know that one of those two things is true. Okay? So let's see. So here we have step 1, step 2, step 3, step 4, step 5, step 6. So let's go through and figure out what happens in the circuit at each time step. So, okay, so obviously step 1, we have the state all zeros. Then at step 2, what have we done? Well, we've done the Hadamard transform on these zeros. So each one becomes 0 plus 1. Right? And the tensor product of 0 plus 1 means that we could have any bit string on these n things, right? Because 0 and 1 are equally likely, so any combination of zeros and ones is equally likely. So at this point, we have sum over x, tensor 0. So now we do the oracle call. So what does the oracle call do? Well, for each basis state, x here, it calculates, this becomes 0 plus O of x. So we now have an entangled state, well, potentially entangled, that looks like this. Okay? Everyone with me so far? Okay. So now, step 4, we do a z. So what does z do? Well, if this is 0, we get a phase +1. If this is 1, we get a phase -1. So we have this state. And then step 5. So step 5, we're again calculating O of x. So this stays x. This becomes O of x plus O of x. Where? Here? No, sum. So up here is the sum, right? Because so it's this is the tensor product over qubits 1 through n of 0 plus 1. Okay? Which means that but what's the tensor product of that? So tensor product of, so here. So let's expand this product. Well, what's the first term is 0, 0, 0, 0. The second one is 0, 0, 0, 0, 1, and then 0, 0, 0, 1, 0, and so on. And so we're actually running over all possible bit strings x. OK, so at this stage, we're adding O of x again to the second register. So it cancels, right, because this is binary arithmetic. So we have this. So this last one is kind of factored out. And so now we're doing the Hadamard transform on this. So at step 6, I want to, at this point, divide up by the two possibilities. So suppose it's constant. Well, if it's constant, then either this O of x is always 0 or it's always 1. And so the phase here is always the same. So if it's constant at step 5, we have either plus or minus overall phase, and then sum of x, x. And we know the Hadamard transform is self-inverse. So doing the Hadamard transform on sum of x, x gets us back to all zeros. So what we have at step 6 then is a global phase, plus or minus, and then all zeros ket, and then this extra one is all 0. And in that case, we do, in fact, output, and we make the measurements, and we get all zeros. And so we output constant, as desired. OK? What happens if it's balanced? OK, maybe this one I should move on to the other blackboard, since it needs a little more space. So what do we have in the case of balanced? Well, let's call this state that we have here psi. Oh, sorry, this one I was calling phi. And psi is the state sum over x of x. OK, so we know that the Hadamard applied to psi is all zeros. And moreover, the Hadamard is a unitary operator. So notice here that the inner product of psi with phi is equal to 0. Why is that? Well, let's calculate it out. Well, we get sum over x of -1 to the O of x. And this function is balanced. So exactly half of the O values are 0, and half of them are 1. So we're adding up plus or minus 1 with 2 to the n minus 1 pluses and 2 to the n minus 1 minuses. So they all cancel. So this inner product is 0. Okay? And what that means is that unitaries preserve the inner product. So the inner product between h applied to psi and h applied to phi is also 0. And in particular, h applied to phi, well, it's going to be something of this form. But we know that it has inner product 0 with this thing. So we know that alpha of all zeros is equal to 0. So we get a superposition of things that we don't really know exactly what the form is, but we know that it will have no component of all zeros. And so that when we measure it, we get something that will not be all zeros, and so will output balanced. OK? So this algorithm solves the problem up there. And it works with 100% probability. It only uses 2 quantum queries, as opposed to the classical case, which used 2 to the n minus 1 plus 1. So that's a big improvement. So this is kind of the first example I'm showing you of where quantum algorithm gives an improvement over classical algorithm, albeit for a kind of artificial and an oracle problem at that. OK? OK, so let's end there. Tomorrow, we will talk about a kind of more interesting real problem, which is factoring. I'm not sure we'll have time to get through all of Shor's algorithm tomorrow, but that's where the kind of the real meat of quantum computation starts to come into effect. Today, you have a tutorial at 3:45, and you'll play with some of these complexity things and algorithm things. OK?